What was compactness again? What's the Borel-Lebesgue criterion? Open. Right. We can have open, closed, and arbitrary covers. A set S is compact by the Borel-Lebesgue criterion if every open cover of S is reducible to a finite subcover. Right. And now that brings us to where we want to be for today to prove the characterization of the compact sets of real numbers. Do you recall what theorem does that for us? What theorem is it that characterizes the compact sets of real numbers? We talked about it at some length last Tuesday. Too many. There's not too many guys. Heine, Borel, Lebesgue, they're all working on this. Heine, Borel. So let's try to prove the Heine, Borel theorem. Given a set of real numbers, S is compact if and only if S is closed and bounded. That's a great theorem. I mean, it's easy to state. It's reasonably easy to remember. So does this mean only closed intervals, bounded intervals are compact? No, you can have unions of closed intervals, right? Just as long as you don't have so many that it becomes unbounded. Right? Okay, close it bounded. So, let's do this direction first. This prompted the great search for sufficiency and necessity. It's necessary for the set S to be closed and bounded. Why? Take S equal to N. Closed, not bounded. Is there a cover we talked about on Tuesday? There's a cover of this that's irreducible. Can you remember what it is? What if the cover consists of sets of the form n minus 1/2 and plus 1/2 and an n? I claim that the union over the cover certainly contains n. So it's a cover. Is cover, yeah. Right? Is it reducible? Who would you like to throw out? Is everyone essential here or not? Who would you like to get rid of? If you get rid of any one of these, what happens? Your little old n is uncovered. Right? So everyone's essential. How many sets are in here? Infinitely many. So apparently, if you're not bounded, you have no chance of being compact. Okay, what about closedness? Take S equal open at 0, closed at 1. And look at this cover. I would like to have sets of the form 1 over n, 1 plus 1 over n. I claim again that the union over the cover of everything is covers S. Is covered, yeah. All right. Well, you need them all. How about wine? Lecture over. You need them all. What were you going to throw out? Well, let's examine, first of all, the claim that this actually does cover the interval. I think it does. Does everyone? It's rather subtle, though, isn't it? I claim that if you pick a number in here, one of these guys will pick it up. Go ahead and pick somebody. Epsilon. Okay? Pretty close to 0. We're sure the stuff that's over toward 1. Right? These things always go out and grab 1. Okay? Pick an epsilon in here. Well, once n gets bigger than 1 over epsilon, 1 over n gets smaller than epsilon, it gets to the left of some epsilon that you pick. So everybody's going to be in one of these, right? Okay.
You can't leave any more of the time. You typically leave out a small round 0.
Well, I could leave out infinitely many of them.
Yeah.
I could leave out odd ends,
Okay.
but I can't ever chop it off and make it finite, because then it would be the smallest 1 over n, and then I would get to the left. Right? But I could leave out infinitely many of them. I just would have infinitely many left. You know, if you chop infinity in half, what do you get?
Same size set.
Infinity over 2, right? If I let n be just odds, they would do the job. That would be a cover. But it would still be an infinite. If I let n be even. If I let n be...
Technically, you only need the last one.
Right. And you never get it. K times a prime. Pick a prime. Any prime. 37. 1 over 37k, k ranging over capital N, would be a weird little set that jumps 1/37th at a time, right?
You choose n only primes.
Yeah, only primes. Factorials would be all right.
I like that.
But the problem with it all is this. There's always infinitely many that you need, and you can never make this finite. You see why, Cindy?
Was it that cancer?
Oh, probably one of many, yeah.
I mean,
I don't think he didn't prove this. Pardon?
Considering I want to contain infinity, I have it all on the interval.
Well, that wasn't the continuum hypothesis, but
No, he's the I think we remember analysis.
yeah. Well, I hope it comes back and not quite so bad. Yes, you're right. The real numbers in this half-open interval, we count them, they're uncountable. That's okay. I can step through them with countably many of these sets and capture them all. Because you know that the rational numbers, for example, are like things like this. Even the dyadic fractions, like 1 over p or something like that, 1 over p squared, 1 over p cubed. Those things are dense. You know, if you take all possible multiples of those things, you can count them, and they're dense in the reals.
That's the bound, right?
No, they're not. I mean,
the number of numbers between 0 and 1 is bound.
Yeah.
0 bound by 1. So you're with the finite number of sets comparable.
oh, getting countable then.
Well, not with these particular sets.
In all hinges, they. Whether that's closed or not.
Just take an interval from -1 to 2. It covers an infinite number of numbers from 0.
Right. But this is not compact because I'm exhibiting a cover of open sets that is not reducible to a finite sum. You can dream up a cover like you just did, -1 to +2, that has one set in it. That's very finite, and yes, it covers it, but that's not compact.
I understand that.
Yeah. Yes, you're
It
right.
has to be universal.
Yeah. Right.
So
So
what's that notation?
where? Here?
Union of covering sets.
Oh, that's covering stuff?
Yeah, the union over this family. That's an alternative. What this means is take the union of all of these. Family C defined like that. So it's a cover and it's irreducible. Irreducible. So not compact. So we have decided that you need to be bounded and you need to be closed. Because because if you avoid the boundedness or you avoid the closedness, you have situations where you're not compact. So that's the necessity of boundedness. Cindy, that's the necessity of boundedness and closure. Now, the hard part of the Heine-Borel theorem is sufficiency. If you do have a closed and bounded set of real numbers, then it is compact. Okay? So the other direction is the real proof. These are just two counterexamples. You can dream on levels. That'd be a good test problem. Come up with a different one. Right? You can do